So two folders as well as the permissions, everything is given here. Now we have something like already the permissions exactly are given in this. So we will change the permission. Now how to change the permissions? So here we have some particular command. Okay, so here if we see this, we will have one particular command called chmod, which is change mode of the particular directory or file. Now here in chmod accepts two options. Either it will be specified as a sequence of 3 binary digits, or we can say not binary digits, sorry, 3 octal digits. So octal digits means you will have something like only it will accept numbers from octal accepts number from 0 to 7. Okay, so when you say 0 to 7, you have 7 combinations, right? Now each octal digit represents the permission associated with a particular digit. Like if you say hyphen hyphen hyphen, so this is represented by 0. Similarly, if you have hyphen hyphen x, it means 1. Next, if you have hyphen w hyphen, then it is 2. Then you have hyphen wx, it is 3. Then you have r hyphen hyphen, now it is 4. Then r hyphen x, 5. rw hyphen 6 and rwx as 7. So these are the 7 permissions we can change. Now, for example, how to change this particular thing? Now, if we go into a particular folder and we will try to change the permissions of it. Okay, so already I said you that here the it particularly represents that what can be subtracted or what permissions can be added other than if you have U as user, G as group, O as other, D as directory. If you see here it is saying that it is a directory. Okay, D represents directory. If you want to see what it can represent, just go into that particular folder. Now if I say cd new, so here do I have something here ls hyphen L. Now if I see there are no files in this, so I can just come back and I can see in this C file. So just enter into the C file, and then if I see this here, you can see that here D is not there at starting. Why? Because here this is not a directory, but these are files. That's why it is just saying that here here D is not there and it is starting from R, W, read, write. Okay, so here if you see, I want to change the permission of some particular file. So I'll just take the last one here, stack1.txt, and we will try to change the permission of this now. Now if you see minus rwx, rwx is there. Now we will try to change this. That means 3 permissions are given to it. So we will first change it by chmod. Now if I give only the 6th one as rw, right, read write permissions, then I'll just make this like 600. Okay, now okay, it's better I'll just create a new text document. Before doing that, it would be better. So I'll just make a text file. So gedit some new file dot c only, I'll write just to save it, and I'm not going to do anything is this because I want to change the permissions and see that how it looks. So here it just a second. So now we will change the permissions for this file. So here we are starting it with chmod. Now I am writing 600, and if you see this here, the 600 is 6 is RW minus and rest of it should be minus minus minus, right? So here I am giving it like the file name. Now my file name here is new file dot. Oh, before that we will just check what are the what is the list here. List hyphen L if I see, and now go to your new file. So here new file dot C where it is. Just now we have created a new file dot C. So here it should be somewhere. Now here if we see, these are the permissions given in new file dot C, and it is created at 8:32 July 25th, right? Now here and here this 0 represents something like what is the size of it right now. So it is 0 because it's an empty file, and right. So it's nothing. Already some permissions are given, right? Read, write, read, write, and read, write. So here we will change the permissions. So you can see here, I think. Now chmod 600 and new file dot C. And now again we will see the permissions. Now if you see here, the permissions has been changed. Okay, so in this way we can change the permissions of a particular file or directory. Okay, so as of now you may feel like what is the need of it, yeah, but coming to next things we can understand that why all these things are needed. Okay, so now next thing we have here is a basic file system concepts. Okay, we have seen some file systems, right? File system in the sense we have seen the structure of our directories. Now we'll see how it is implemented. Okay, so basically they are implemented with the concepts which are from Unix, because Unix is almost equivalent to Unix is a Linux is like invented in place to replace Unix. Linux is an open source and Unix is not, right? So Unix or Linux has been implemented to simply adopt the same things or all the concepts which are derived from Unix, but it's an open source. Okay. Now here you have two things like inodes and directories. Okay, directories already we have seen that they are nothing but folders and contents of files. Okay. So what are the list of entries we have, and so we can just access those by using this IO operations. Now coming to inodes, when each and what is this inode is? Inode is particular number. Okay, it is a unique number to unique file. So whenever a file is created, an inode is also created. So this inode, a file name as well as an inode is created. This inode is a number, and file name obviously we are giving it. Okay, so this file is given two things. One is file name and the other is this file name as well as inode. Now here what it's a simpler data structure. Okay, it contains some information about your file. And one more thing you will have is this inode does not contain your file name. So when you are accessing a file, you are accessing it through file name, but internally it does not use that file name to access that particular file. It uses the inode. Okay, now what does this inode or this data structure contain? It contains different information like what is the user ID you are using, group ID, and then device ID, full size of this file, date of creation, what are the permissions given to this particular file, owner of the file, if at all if some protection is given for that file, then what are those protection flags used. Then you have something like yeah, so all these particular things are all these things are stored in this particular inode. Okay, now how to see this inode or how to find out? Now if you see, we have just created one particular file called new file.c. So we will just see now here if you see this, just use this list again. So list -l and d and then give the file name new file.c. Now if you see this, the permissions as well as whatever just now we have done, we got that thing, right? Now this is nothing. So this is nothing but your inode. All these things are your inodes which are there in your all the informations, all these informations will be there in this inode. Okay, now you may have different inodes. So many inodes are there. If we want to see how many inodes are there and how many inodes are used or left, we can see that by using here inode number is not given. Okay, so here you will have some particular numbers related to particular files. So we will see that now. So for that, what you need to do is we need to use command that can be used. So here we are using df, okay, and -i. Now if we see this, see, these are the file systems we have. For each file system you will have some particular number of inodes, and here these are the used inodes and these are the free inodes, the percentage of inodes used and where they are mounted on. That means this particular now if we dig into it, what we will see, now here what we have, now if you see this, justice, okay, so here we have file system used. Okay, now here all the informations has been given about your inodes, right? Now if I want to just find out something more about it, so I think this will be enough, right? These are the inodes related to it and you can find out numbers. Okay. I want to dig more into it, so I'm just thinking of some more commands. Okay, we got it. So here you have, now when you see this, here you have total number of 168. There are not files, okay. Why? Because we don't have this 168 files. So here we have, if you see, these are the numbers given to it, inode numbers we have. So when you are accessing a particular file, this will be used. This will be used to access that particular file rather than name of the file. Okay, and if you see, these are in sequential order. Okay. Coming to next thing we have. Okay, so one thing we have left, and that is, first of all, I want you to know that what is an open source thing. Open source is nothing but when you are using some open source, or if you have created some open source file that can be read, write and distribute openly. That means it's not commercial, I can say, or you can say when you are creating now Linux. Here you have something with Linux, like I have this version of Linux we are using. So if I want to change the form, if I want to change how it looks, or I want to create something new in this, I can edit this OS itself. Okay, so Linux gives the permission to edit the OS. Edit the OS in the sense, here you can make some changes, or if you have some bugs in particular in OS or in any applications given, then it allows you to fix it. It's not necessary that a particular person has to fix it. So anyone can find out an error, anyone can create new things and add into it, or if I want to change something into this, we can do that. And but the only thing it does is, if we do some changes in it, it should be visible to all, and someone else should also be able to make the changes we are adding, or it should be accessed by everyone. Okay, so it's completely open. So when you say everything is open, you are able to see everything, you are able to read, write or change the permissions or change the code. We say it like it's an open source. It's free, completely free, and you can just use it and just to change according to your requirements. Now, what is the advantage of using this Linux actually? Why we should use this? Why? What is the use? So first of all, Linux is free. Okay, when you are using some Microsoft or Unix-based operating system, Windows. So what happens? We need to find a license for it, right? So here it is completely open. It's completely open. There is no need just to download the software and run it. That's it. So it is free. And here the license which they use is GNU Public License, which we call it as GPL. GNU Public License. And what is this GNU is? GNU is not Unix. Okay, so particularly the full form for this they use is GNU. It's not in Unix, so this particular OS is not a Unix. Okay, so GNU is not a Unix, and they use this license called GPL, GNU Public License. So what does this license say is, anybody who wants to use it has the right to change the Linux. Okay, and redistribute it. So after making the changes, you can say that okay, my this particular version is good, so you can just redistribute it. But whatever changes you have made, that code has to be visible, right? Then now the other thing we have is, one is it is free, second it is portable, so you can use it on any hardware. Third thing you have is here one good advantage of it is we need not restart it. Okay, so here we need not reboot it continuously. Once you log in, you can just keep it on all the times without rebooting it. This is one of the advantage we have. and that's why it can be used on embedded. Okay, why? Because there is no need to reboot it. Next, you have is it's a secured one. Linux is secured, and the security model which it is using is based on again Unix. Okay, next you have so as it's an open source, if you find any bugs on it, it can it can be just debugged in very short time, because many people or thousands of people are using it, and that's why the solutions are rather found quickly, very quickly, rather than taking time. Okay. So once you find a bug, report it, and you will find the results very fast. Then, oh, so as I said, here you have some GNU tools or anything GNU, right? GNU is not Unix. So here you have when you find your system or when you install a system, some software, common softwares are available for this GNU. So it can be like compilers, your screens, shell screens, compilers. Then you have some editors. All these are common GNU softwares which are completely free. Okay, but there are now there are some applications which are there at commercial basis also, but all these are the free things. Now, here you have okay. So now we will continue with this. Now, one more thing. When you want to find out about particular commands, so how to find out that particular command is simply using something like details about the command. So that details of the command can be used by using a command called man, which is manual. Okay, we will see that also for a particular command. Okay, so now coming back to the discussion we had a day before or 2 days back, we have some subsystems in kernel. So the subsystems are your process management, memory management, file management, device I/O management, as well as network management, and these uses something called system call interface, which is a connection between your kernel as well as your user space. Okay, so they use some system call, right? So if you say any application is there in user space, in kernel space, you have device driver. So to access that device driver in between the user application and system software, we are using system calls, and the kernel that accesses, that communicates with your hardware. Okay, so till this it was all okay. Now coming to the next thing, here we have something called a process. Now what is this process? So here what is the process? When you are writing a program and then you want to execute it, at that time when you are executing, we are loading that program into RAM, okay, for execution. When you are loading a program into RAM for execution, it is called a process. Okay, program which is loaded into RAM for execution is process. Okay, So any program, when you want to execute it, how we will execute it? Simply we are using something like we are writing one command called gcc, and we are making first we are using some compiler to compile this program, right? So what we are doing, gcc something like new file.txt, and thereafter what? So here when you execute this command, an output file will be created, right? So as we are not giving any name for this file, already I have said you that we can create a different name for this file. If we are not giving any name for the output file, we will get a name with a.out, right? So this a.out is executable file. Okay, so this when you are running it, this is when you run this a.out, this is loaded into your RAM, and that you call it as process. So any program which is on execution or which is loaded in RAM for execution, we call it as process. And now we will be writing different process, or we will be seeing different things related to this. Now this executable, which is a.out, where it is stored on hard disk, right? So as of now what we are doing, we are storing it in same folder. So we are storing it, or we can say that we can store it either on anything like either your anything in the sense on hard disk or any external storage device anywhere. Simply a.out takes some space. So when you are storing it somewhere, and again when you want to execute it, it has to be loaded in user space of RAM. Okay, even if you store it anywhere or on same folder or anywhere, what we are doing, we are loading it into RAM. So where in RAM? In user space of RAM. Again, in user space of RAM, we are loading this program. When you load it, then only it will be executed. Most of the time, user is creating process. Okay, because I am writing, right? So when you are executing a file, user is executing a file. So what we said, whenever we are executing a file, it is loaded into RAM for execution, and we calling it as process. So basically you can just frame it like process are mostly created by the users. Okay, but some process can be created by OS also, but most of the time we are creating it. Okay, so this was about your process. Now, how to manage this or process management system? We have this particular subsystem, right? So coming to your process management system now, what does this do? So already we discussed it that process management system that process management system, what does this do is it manages the process creation, deletion, if you want to suspend the process or resume the process, and other things we can do with this are like create, delete, then yeah, that's it. Create, delete, suspend or resume. All these things are done by process management subsystem. Okay, now we can have so many processes running in user space. Okay, that means we can do multiple processes running simultaneously. We can do that. Okay, now here you have one thing like what else it is providing now. what else it will do is it will also communicate. It can also be done something like you can communicate between different multiple or different processes running in user space. So if I am running multiple, I said that we can have multiple processes running in user space, and the process which are running can have communication between them. Okay, and you can even share the data between the running process. Okay, that means the process which are running in user space can share the data as well as communicate with each other. The other thing it provides is it can have synchronization between different processes. And you will have something called deadlock handling that is also managed by your process management subsystems. Now, if we just have this as a point, you can say that process management system manages to create a process, delete a process, suspend a process, as well as resume a process. Then we can have multiple. It also manages to have multiple processes running on in user space, and it provides some mechanisms to communicate between multiple processes which are running in user space, and you can share. It manages how to share or share the data between the multiple process, and it provides mechanism for synchronization and for deadlock handling. We'll be saying it one by one. Now, for example, if we can say that when you are writing some process, so you can have scanf in it. Okay, when you use scanf on your screen, you will be waiting for some time. Okay, when you till when it will wait? It will wait till you enter an input, right? So till you get an input, it will be in, you call it as blocking state, because you are simply blocking that particular option. Okay, when you are using scanf, it will wait. That is called blocking. That is in blocking state. And similarly, when you say one more thing, sleep option is there in our Windows, right? Sleep is also a blocking state. So it will wait till user enters an input. Okay. Next you have is memory management system. These are just an introduction I am giving, right? So what does this memory management system do? So here you will have two types of memories, right? One is primary memory and the other is secondary memory. So primary memory can be something like RAM, okay, and secondary memory can be like hard disk, right? So hard disk, you can call it as secondary memory, and primary memory is RAM. Now, if you see in our systems, general laptops or any systems, always RAM is less than hard disk, right? You can have RAM of somewhere around, starting from previously we used to have around 512 MB. We have 1 GB RAM, 2 GB RAM, and nowadays we will have even 64 GB RAM, I guess, 16 GB RAM. We can just extend that. So here we have that much RAM memory available. But when you go to secondary memory, you can have in terabytes, right? So it is not just it is not restricted to somewhere like 16 GB or 32 GB or 64 GB. The hard disks are available in terabytes. So you can just make a conclusion that always primary memory is less than secondary memory. Okay, so primary memory is always less than secondary memory, but primary memories are faster than secondary memories. So speed wise, this is like when you say size, size is always, in size terms, primary memory is always less than secondary memory. And when you say speed, then in speed wise, primary memory is always greater than your secondary memory. Okay, why? Because obviously the size is less, so the speed is more. Okay, and other things which it does do is it allocates. Already we discussed it is using something like MLOps and all to allocate and free the space as needed. Okay. And one more thing it will do is, this memory management subsystem will do is, it will just keep track of the memory which is used and by which process it is used. Everything is seen by this memory management subsystem. Now, if you remember, we have something like binary file, how this a.out file look like. Okay, when how this output file look like. So that you call this memory segment. Okay, what is this? It can be a.out or ELF format. ELF is nothing but executable file format. This ELF format is for Linux. Okay, so what we have, if you remember, we have some memory segment or a.out file looks like we have heap, stack, then we had text or text, we had data, BSS, and we discussed that the data does contain initialized static and global variables. BSS contains uninitialized static global variables. Then text code contains whatever functions we are writing or text. And other than that, we have stack and heap goes down and stack goes. Sorry, stack grows down and heap grows up, right? Now, by default, when you are creating this, we don't have stack and heap. Okay, this is created when this file is loaded into user space of RAM. Okay, so by default, this stack and heap, if you remember this, I can just show you that image of it. A.out. Just a second, I am downloading an image. Memory segment structure. So now if you see this here, you have command line argument, then you have stack which is growing downwards, heap which is growing upwards. This is static memory layout which is uninitialized data section, initialized data section, and text code. Now when you are creating a process, by default we don't have this stack and heap segments in our program, but when you load it or you just make this as process, this a.out file is loaded into your user space of RAM. Two segments are created. These two segments will not be there by default, which means that dynamic memory layout, which is indicated by this stack and heap, is not there by default, but when you start executing it or load it into user space of RAM, these two are created. Okay. Along with this, now you know already that how this grows. It grows when you are using some dynamic functions, and stack is how the stack grows is when you are invoking a function. There, if you have some variables, it will just uh, create that particular things in stack, and it is stored, right? So now, along with this, in kernel space of RAM, one more part is created, and that part we call it as PCB. Okay, now what does this PCB contain? So I'll just to show you the pic of PCB also. Mm, we uh, mm, just a second. What is the structure of PCB? I'll show you. I hope it's audible. I'm just sharing the screen again. Automatically it has the layout done. Now, coming back to your PCB, I said this is process control block. Okay, so what is this content is, this process block control contains some information about your process. I hope it's visible. Okay, so what does this contain? It contains something like process number, process counter, register, memory limits, and some status data and everything. So basically, actually, it contains in simple language about your process ID. So with each process, one particular ID is related. Okay, so that particular ID we call it as. So first of all, here this PCB is nothing but process control block. Process control block, and this is created along with your a.out file. Okay, this is a kernel object, and what does this contain? It contains some members, and it is a type of structure, and this structure contains some particular members. That members, many members are there. Some members are like process ID, which is nothing but we call it as PID. Why I am writing this down is because we will be using it in our program. Okay, so that should not be confused. Is attached, and we call it as process ID, and then you have parent ID. So parent ID is like who is the parent of the process created. So if you have any parent of the process, that means you are creating a process from a process here, that is your parent process, and that you call it as PPID. And then you will have some file descriptor. In that file descriptor you call it as FD. File descriptor table you will have file descriptor. Then you will have some page table. All these things, it might be confusing right now. Why? But we will be seeing it in detail. Okay. Then you will have something like signal disposition table, then signal task, process state. All these things will be there in this particular process state. So all these things will be there in your PCB. Okay. Then now, so whatever predefined functions we are using, okay, that is stored where? In library, right? So when you are storing it in that library, what happens is it has to communicate with your kernel object, right? So first of all, what it will do when we load an application in user space of RAM, a block of memory is created, okay, along within user space of RAM in kernel space of RAM also. Okay, so user space contains your a.out structure, and the kernel space contains your PCB table. Then what will be the type of this structure? I said that here this contains a particular structure, right? Your PCB does have some structure, and so the structure will be something of type struct task underscore structure type. Something will be there. We will just see that later. So this will be the structure type. Then, so when we have this user space as well as kernel space of this particular memory added, combination of this we call it as process, because when you are running a process, both will be running in RAM space as the user space as well as kernel space. That particular whole thing, a combination of both is your process. Now, what is this process identifier and all we will see now. So if we want to check that what are the running applications right now in user space of RAM, we can do that by running some commands. Okay, just now I said that some processes are already running. We have so many processes. So right now we are not using any a.out, but by default when you are running an OS, some process are created by users and some process are created by your OS. Okay. Why I said mostly user is because we can only see that, but internally your OS creates so many processes. So we can see that by simply writing one command called ps-ef. Now, when you click on this, you can see that you have these many processes running in your system. Okay. Now, if you see, this is UID, this is PID, this is PPID, then you have this time and command. Okay. Now, here, what are all these things? We will see that. If you see the first thing, your PID. So here right now we are interested in this PID. Okay. Now PID is your what is it? Process ID, right? So if you see this, no process ID is same. That means all the process will have different process ID. No process ID is same. Every process will have a different process ID. Okay, but you can have same PPID, which is parent ID. Okay, if you see here, there are so many. If you see here, 222, everything, everywhere this 2 is given. Okay, so all these things are your PPID. So you can have same parent, but process ID will not be same. Okay. So we will see all these things. Now, what is the first process which is loaded? So we can say that now on a whole process we can say that whenever you are starting your user, when you are starting your OS, right? So many process are starting at from start and it will be there till you shut down your system, which is started by your owners. Okay, so what will be the first process that is loaded when you start your system or boot up time? That process you call it as init process. Okay, so on the first program or first process that is loaded at the time of boot up, it is init process. Okay, and this process will have the process ID as 1. Okay, init process will have process ID as 1. If you see here, what is the process ID 1? So here if you see this particular line, you can see that it contains something like init flash. Okay, so always this particular init will have process ID as 1 only. Process ID is 1 and it is there in something like sbin init flash. Okay, so just remember that the first process that is loaded during your boot up is your init process. Now, this process creates multiple processes. So when it creates multiple processes, it becomes parent process. Okay, right now if you see the PPID, here it is 0. Okay, so here you have whenever a process ID, I would say, whenever a process creates multiple processes, that you call it as parent process. Okay, so here if you see somewhere we can see even one is your init. So that is init creating some other process. We can see that by seeing PPID. Okay, so here if you see this one, here you have this 216th one is created by your PID. Sorry, init, and here you can see these are some of the processes which are initiated by your init process. Okay, so when you create some multiple process, you call it as PPID. So your init becomes your parent process. Here every process is created by some other process. Okay, every process is created by some other process. Why? Because if you see here, you will have some parent ID attached to your process ID, some or the other. That means every process will have a parent ID. Now, if you say, for example, this terminal itself. Now, when we are opening this terminal, we are using some process, and that process is your bash process. Okay, so that means what? When you are using this bash, using the bash process, you are using this terminal. So terminal's parent is your bash process. And every function or every process which is invoked, every function which is invoked, it is invoked by a system call, which in turn invokes your kernel. Now, here we are opening some particular number of files, right? Now, all these particular number of files is all this particular number of files opened. That information is stored by a table called FD table. Just now I have given you something like here FD table, right? In Notepad I have just written FD table, and this we call it as file descriptor. Okay, so all the files which are opened, the information about it is maintained in this FD table. And one more thing you have to remember is, whenever we are saying that a table is maintained at a particular particularly by kernel, then it is a structure. So always it will be a predefined structure, and it will be of type something like array, or just now we have written task underscore structure, something like that. Okay, so always at this kernel state, if we are saying a table is maintained, it is a predefined structure. When you say a page table, okay, we said even page table is also it is there in your process PCB, process control block. So what does this contain? So this page table needs a concept called virtual memory. Okay, so we will have two things in this virtual memory: paging techniques and address techniques. So here, when we just we will go to this particular techniques, then we will be able to understand this particular virtual memory concept, and in turn this page table concept, which we will see now. If you are creating n number of process, okay, so if you are creating n number of process, then n number of user space in RAM is created, as well as n number of PCBs are created in kernel space. Okay, that means if you are running 10 programs, then 10 user space as well as 10 kernel space of RAM is allocated for your process. Now, if I say that n number of PCBs are created or n number of processes are running, that means we should have even a list of that PCBs also. Okay, so that are maintained as linked list. Okay, they are called running queues. Running queues. When n number of processes are running, n number of user space RAM as well as kernel space RAM PCBs are created, and the information about all these PCBs are maintained as linked list. Okay, and they are called running queues, and they are maintained by again kernel. And one more thing, if you are running n number of processes, then your CPU allocates equal amount of time for each process for execution. You have to remember that processes are not running simultaneously. They are running one after the other. So your CPU allocates particular number of amount of time for each and every process. Now, if the process, whatever it is running, is completed, okay, the running of that process is completed within the CPU time allocated to it, then simply it is terminated. The process is terminated, okay, and whatever that corresponding memory segments are created in your user space as well as kernel space of RAM, it is removed if the execution is completed within the specified CPU time. Okay, if at all if that process is not completed, then what it will do is, as I said, it will just run one at a time. So it will suspend that particular process for some time, and then it will jump to the next process. It will execute that, and again it will jump to the next process, and after that n number of process, again it will come to your first process. So the process goes on like this. So it allocates one particular time. Now if I say I have 5 tasks running, so and my CPU time which I am allocated is 10 seconds. So first 10 seconds it will execute our first process, then it will execute our second process, then third, and then fourth, and then fifth, and again it will come to one if at all if that process is not completed. In between, if some process is closed at that time, this then what it will do is it will just remove the user space RAM as well as your kernel space, and this process will be deleted. So this from 3 again it will come to 5, like that it will continuously run. Now if we want to create a process using another process, just now I said you that we can create a process. Every process is created by some other process, we said. Just now we said that every process is created by another process. So how to do that? We are using a system call for that. Okay, that system call which we are using for that is fork system call. Okay, so fork is used to create a process from another process. To create a process from another process. Till now there are no doubts, right? Now, when you are using this particular system call, it will send request to various subsystem calls of your kernel. Okay, like you can say that you want to, you are using directly fork, you cannot use. So when you are using fork, internally it will be using some system calls which is equivalent to your kernel calls. Okay, so this will use internally something like sys underscore fork. Okay, or if you are using some function called open, at that time it will be using, okay, when you are using a system call called open, at that time internally the kernel will use system underscore open. Okay, so internally they will be using this function calls. Now, how it will work? So, when you are using fork function call, fork will send a request to create a process. So, fork will call internally sysfork. Okay. So, sysfork, fork will call, fork will make a call to sys underscore fork, and sysfork will request your process management. Okay, to create another process. And then this will again do the same thing, either create a process, destroy the process, suspend the process, resume the process, share the data, or synchronize some or the other. This will do. Now, when you are creating a process using fork system call, you call it as child process. Okay, using fork system call, if you are creating a new process, then you call it as child process. Child process, and the from where you are creating, or the program in which you call you are using this fork is called parent process. That means when the process which is using this fork to call a new process, we call it as parent process. Process which uses fork to create new process, or new process is your parent process. For example, here we can write it like, now I am taking a variable called id, okay, and then this, using this id, I am just creating a child process using fork, and then I am writing if this ID is equal to 0, then what we are doing is do some particular. Okay, we can directly do that by writing program, right? So we will just create one folder now. On desktop, we will mkdir is the command to create a new directory or a new folder, we can say, and we are just writing here Linux. And change directory. CD is the change directory to this Linux folder, and here we are creating one new process. Okay, so we are writing like gedit. Process 1.c. So here we are writing our program. Now what we are doing, we are taking one variable called id, and we are using this id equal to for system call, and then we will write if this id, that means what, if the fork executes successfully, then this id will be given that particular, it will have one particular id. Okay, so that means a child process is created. If at all, if that is created, do some particular work, else yes. So here if the sorry, okay, now when you create this, so if the id is 0, here we are printing something like process id is 0. I'm just writing it just for as an example. Okay, else printer child process, we will just print this id. Okay, child process id is equal to %id \n comma id. Okay, now we will see that whether this if is executed or this else is executed. So gcc sys1.c. So here we have some warnings and we will see that later, but as of now we will execute this dot. We have not included stdio.h, actually it started from main directly dot slash a dot out. Now if you see that here it has been executed that when you executed this a dot out, here it's given child process ID is 2436, and then again here child process is 0. 2 times it has executed. Just a second here. So here if you see, again we have created one process and the ID is 2484. Previously it was 2436. Now 2484. Again if we create a different process, you will have different child process. Okay. So here now when you create a child process with this 2484 or 2436 process ID, already one process we are running it using /a.out. So along with this, one more PCB as well as one more child process user space RAM is there. So again it will create two memory segments. One is user space and kernel space of RAM, and one will have a process parent process ID, which means the process we are executing, which was a.out, and one more child process which is 2436. So two blocks of memory will be created, one for parent and one for child. Okay. Now if you see the PCB of the child process, then what you will have is the parent ID which we have. So that means a parent ID will be there for a.out. Okay. That a.out will, in that a.out, suppose your a.out is something like parent ID is 2000. Okay. So the child ID is now 2484. So in this PCB, the parent ID will be 2000 in child process PCB. The rest of the everything will be same. We have PID, PPID, everything, right? If we see here, the process ID as well as PID. So just now we executed this a.out. So if at all, if the process ID of that a.out is 2000, then when you create a child process, that child process parent ID will be 2000. And some more particular things of this parent ID will be copied into child PCB also. Like for example, this FT table, page table, everything, these things will be same for parent as well as for child also. And memory segments are also same in the child process. The child process will be almost a replica of your parent process. So basically if we see our program right now, we can have so many fork calls. So our parent ID or our one process is creating any number, n number of fork calls. If we do, n number of childs are created. That means n number of processes are created using one single parent. Now, if we want to execute or if we want to see that parent as well as child are executing same code, we need to just visualize this. Okay. Uh, we are seeing that the same code is being used by your process parent ID as well as your child. Your parent as well as child are executing the same process but at the same code, but actually they are different codes. Okay. Now, mm, till now, is it clear? I hope it is clear. So when you write this particular program, here what happens is, when you call this particular fork, okay, it returns the values both for child as well as for parent. Okay, then the child process starts executing. That means after whatever you are executing after your fork call, that is your child process. Okay, child starts execution after your fork call, and your parent's execution starts from main function. Your main process, or you can say the parent starts execution from main and child starts execution from fork. So basically you are executing your code, your child does have some particular code, so that particular code after fork we are calling it as your child thing. Every fork call, it returns a PID of your, even we can display that also, we will display that. Now, so now when you say you have created a child process from a parent process, right? Two processes are running simultaneously. These two processes will have two particular equal amount of CPU time allocated. Okay, that means either your parent is executing or your child is executing, right? That means if either, now if I say if or your else, so at that time here this, either this if is executing or this else is executing. So either the child is executing or this parent is executing. So if any one of it is executing, that means they are not executing the same code. If at all, if your parent is executing this, if then no, if the child process is executing this, if then this else is for your parent process. Okay. Now, if you have this, if we have seen this fork, so here what happens when you use this fork system call, at that time it will invoke a kernel corresponding kernel call, and that is your sys underscore fork, and then this will call your process management subsystem. Okay. Now if you want to see what else it does, we can use, I said you can use a manual for that. So we can use this manual code, just to whatever you want to see, whatever functions or whatever command you want to find out what does it do, just type man manual and just click on the command. So you can see that here fork is there. What does this fork do? Fork creates a child process and it is included in these two particular files. Hash includes system types.h and uni std.h, and here you are creating it like PID underscore T fork. Okay. Now if you see here, uh, if you see the description here, fork creates a new process by duplicating the calling process. The new process is referred to as child process and the calling process is referred to as parent process, just now whatever we have discussed. Then see, here also it's given the child process and the parent process run in separate memory space. When you are using at the time of call, both the memory spaces have same content. Okay, but after it executes, it will have different. Then it will change the data. Then now here you have one more thing. The child process is an exact duplicate of the parent process except the following points: unique ID and parent ID, because when we execute your a.out, it does have some different PID. Okay, and your child process will have the PID of a.out which we just executed. And child's parent ID is same as parent's process ID. The child is not. Okay, that's it, I think. So these are something which is there, we will be seeing. So you can just read all these things if you want to just dig deeper. Now here you see this return value. What does this return? On success, the PID of the child process is written in the parent and 0 is returned in the child. Okay, so here if you see, if at all, if the fork call is executed, then the PID, that means PID is process ID, right? So process ID of the child process is returned in the parent. That means here whatever is there in this program, what fork is executed successfully, a particular value is given to your PID and 0 is returned in the child. And if at all, if the process is not created, -1 is returned. That means either you will have a particular value for PID or -1. And when you say -1, then I just want to quit this. For quitting, you have to use this Q. Okay. So here we will include that hash include std.h, such that particular warning for using fork call is PID as well as PPID of this particular process created. So by default we have two different function calls for that. So here the function call which we can use to see that is get PID. Okay, and the other function call we have is get PPID. By using these two function calls we can see that what is the PID and PPID. So now here this function returns a particular value and that is of type PID underscore T and here PPID underscore. And almost PPID underscore T, and one more thing you have here is this is type defined. Okay, this is type defined. PID as well as PPID is type defined to int. Okay, so PPID as well as this PPID underscore T is type defined as here integer. Here if you see this, we will see one more thing now, how this is working. This is like man get PID. So here if you identification, okay, and it is included in this particular header file, and so here if you see PID underscore T and get PPID returns the process ID of the calling process, and get PPID returns the parent of the calling process. And one more thing you will have is, okay, that's it. So this information is enough for us right now. The errors which we can have in this, generally these functions are always, so mostly we may not get errors. Okay. Now what happens if at all, if the process is terminated before the child process gets terminated? Okay, that means we didn't close the child process, or we didn't kill the child process, and before that we just closed our main process or our parent process. At that time that child process is called orphan process. Okay, if parent process is terminated before child process, then the child process orphan process. Okay, and we discussed that every process will have a PPID, right? So this orphan process will have parent as init process. Okay, so this orphan Now the orphan process. For orphan process, the parent process is init. Orphan process parent is init. Okay. Now here we are just calling this, and we are taking some more variables here equal to 1 as well as some c equal to 1. Okay, and then we are just making this as here and declaring it as global variable, and then we are calling this fork system call, and then if this id is equal to 0, we are writing one while loop. Okay, so while my I is less than 10, display this child process. Okay, and then printf I plus. And here itself we are printing now printf child process PID is equal to %id \n, comma, we are calling this get PID function, and the parent PID also we will print this PPID, get PPID. Okay, else, in else what we are writing is while my c is less than 10, here we are saying this as parent process, and if we want to display this parent process, we will simply write parent ID, so PID, and here we will write here get PID. Okay, here our while is closed. This is there. Then okay, 1 minute, I will just write one more thing here in this, and then we are using one call called. Okay, and then we are incrementing this because we have, I just closed this without incrementing or decrementing this. See this, right? And then we will just display this later. So we will just call this as, like here we are calling child process. Here I'll just call this like, I'll just print this, but we will print it like Control-C. After this I'll print it, but here we will write parent process. That's it. Now, one more here I write, and this is like parent process ID is percent ID, get PID, and one more here we will write is get PPID. Okay, so basically here what we are seeing to see now. So this is first, this else, that means here we have to close our main function. Now, okay, this is our for main. So now if you see, I hope this program should be clear after executing it. So first I'll execute it and then I'll explain you this program. Okay. See, we have given one thing called sleep. Sleep 1. Okay. Now, sleep is one system call when you want to suspend the process for some particular amount of time. If you want to stop or suspend the execution for some time, then you use a sleep call. Like we have written one function in microcontrollers like delay function. So here we have a sleep call, and whatever time you give in that particular parenthesis, that is given as that argument, it takes it as per seconds. Okay. Now if we don't write that, what happens we will see. Now I'm just commenting this sleep, then nothing will happen. Okay, just see, it stopped executing. After some particular amount of 1 second time, the parent is executing. Now here you need to observe some things, and those things are, first of all, PID. PID is 2763 and parent ID of the child is 2762, which means the PID of the parent has to be 2762. So if you see here, the parent ID of the parent process ID is equal to child's PPID. The PID of the process, main process, parent, PID is equal to PPID of child process. Okay. And if you observe, then here what happens, first it is executing your parent process, and then it is executing your child process 10 times. Okay, so it is executing your child process 10 times. That means what we said, either one process is executing at a time. So child process is executed 10 times, and after that here your parent process comes, and your parent process is executed. Okay, so it's already 10:15. I'll just stop here for today, and then I'll just continue tomorrow. And we have to discuss some more things about this program itself. Why? Because when we remove the sleep, why it didn't execute executed or why it was waiting and then why it created when we are using sleep, it is just executing after 1 second. And one more thing we need to discuss here is your why it is executing both. Actually it is executing both if as well as else, right? So how it is executing, we will see tomorrow. Okay, I hope today's class is clear. Why? Because these are the basics which we will be using to create new process as well as write new programs. Okay, so then let's see tomorrow. I'll just share, I have just converted all the videos in video format and I'll be sharing it with you. Just download the videos today such that tomorrow there's no problem for recording things. Okay. Okay then. Bye.